In the macroscopic world, the motion of an object is deterministic. The effect of the atmosphere on its motion is negligible. However, if we shrink this object smaller than a cell, the motion of the object becomes stochastic due to the surrounding air molecules. This stochastic behavior is modeled by a random walk. Random walks are ubiquitous in nature, have many applications in biology, finance, chemistry, computer science, and many more disciplines. Random walks also have many variants. The walker can be in a 1D space, a 2D space, or a 3D space. The walker can have a probability R to reset to its starting position. But in this presentation, we will consider the one-dimensional biased evanescent random walk on an N cycle. So sounds complicated, doesn't it? So let's break it down bit by bit. So first, let's start with a one-dimensional N cycle. In a 1D N cycle, we have N nodes connected to each other on a circle. These nodes are denoted by numbers from 0, 1, 2, all the way to n-1. Now we introduce the one-dimensional biased N cycle, where now the walker has an unequal probability 1 plus x over 2 to move clockwise and 1 minus x over 2 to move counterclockwise. Lastly, we build up to the one-dimensional biased evanescent N cycle. Now in each step, the walker has a probability of surviving the step given by rho of s over rho of 0, where s here is the number of steps the walker has taken. This is the system we will be investigating. There are many properties we can study in a random walk. The properties we will study are the transition probability, the probability mass function of first passage time, the mean absolute value of displacement, and the expected number of distinct sites visited at least r times. The methods we will be using are generating functions, absorbing nodes, and similarity transformations. So here are the preliminary results. So the transition probability approaches steady state for an immortal walker and decays to 0 for an evanescent walker. For the PMF of first passage time, the immortal walkers is greater than the evanescent walkers. The mean absolute value of displacement approaches steady state for the immortal walker, but for the evanescent walker, it approaches 0 when the walker resets to 0 and steady state when the walker remains in the place it died. Lastly, the expected number of distinct sites visited by an immortal walker are greater than the evanescent walkers. So, this is the exploration properties of the biased evanescent random walk on an N cycle. So we're thanking you for watching.